I'm from Saint-Gobain. A very brief overview about Saint-Gobain. Also about me, I'm a business development manager. Um, my focus is on the EV battery space. So we work on solutions for the battery pack design. So we directly work with OEMs and tier ones. We have another group within our business unit focused on ESS, but our focus has been for automotive OEMs and working with many tiers or also giga manufacturers or gigafactories to provide solutions for cell to cell or pack design. Saint-Gobain in general is French multinational organization. We are about 350 years old, started off as glass manufacturers, and since then we have diversified significantly. One of the sectors called as high performance solutions is where I work at. There are several business units within this high performance solutions providing high performance ceramics, high performance polymers, and abrasive materials for construction, mobility, and industrial applications. Saint Gobain's culture is highly driven by innovation. We have 8 transversal R&D centers globally, and there's a lot of emphasis for research and innovation. So there's a saying within our organization that 1 in 5 products didn't exist 5 years ago. So we are on this constant path of innovating for our customers. Our unifying purpose is to make the world a better home. So some of the global challenges like decarbonization, resource preservation, and rapid urbanization are opportunities which Saint Gobain's can provide good solutions for. And within Saint Gobain, the business unit I belong to is called Tape Solutions. We are more focused on the automotive and aerospace markets, construction and industrial markets as well. We provide several bonding, tape, and foam solutions. Within Tape Solutions, as the EV industry started growing globally, we focused more resources and formed a strategic business unit within Tape Solutions focused on EV or e-mobility customers. So that's where I've been working on. My background is in R&D. I'm a materials engineer specialized in polymer science. So for a majority of my career, I almost 8 to 10 years, I worked on polymer foams, bonding tapes, thermal interface materials, either developing them or manufacturing. I've been on both the sides. Most recently, I took on this position in the commercial team as a business development manager. So I'm kind of a technical interface these days to our customers and our internal functions. With the EV space, the needs are very different, and we can say that the market is very agile. Every customer has a unique battery design or a pack design, so finding the right solution which works for them has been kind of the focus for me and my group. So with that background, I want to give a little bit of introduction on why is compression important in cells, and then talk about thermal propagation, and then introduce our strategy about providing multifunctional materials which combine both the mechanical and thermal properties in cell to cell and pack design applications. So to begin with, uh, maybe it is preaching to the choir to some extent, but I would like to just start off with this background. There's a very nice study which talks about stress evolution and how it is related to the capacity of batteries. So if you look at the cells, depending on once the cells are made, once you start using them, there are several types of swelling which you will come across. The first one is reversible or cyclic breathing, which happens during a normal charge and discharge cycles. So the thickness or the gap between the cells kind of varies, but it's not permanent. It could be reversible. And then there is another part of swelling which over time, from the beginning of your life to the end of your life, your cells kind of lose some of the thickness or increase the gap between them. So there are two phenomena which is normally going on once you start using the cells in a pack. And then using the right material to manage these two is kind of very critical. Why? Because many of the battery cells require some amount of pressure to function, especially if you look at some new technologies like silicon based anode, they really require some amount of pressure. Same with solid state batteries. With NMC and LFP, we are just dealing with normal charge and discharge, reversible cyclic breathing. So, irrespective of the cell type, the crux here is that there is some pressure requirement. You apply too much of pressure over a certain period of cycles, you can see the capacity decreasing. Here, this is the top curve. Whereas if you apply the right amount of pressure over prolonged cycles of charge and discharge, you can see the capacity kind of stabilizes or doesn't drop down as much. And in layman's terms, translating that capacity to the mileage or the range, it's very, very important to have the right amount of pressure on your cells. So, with this background, we want to see what are the factors affect the cell performance. What else can change or impact the range of your vehicle or the capacity of your cells? So the first one was just the cyclic, reversible or irreversible breathing. The next one is the type of anode or cathode you have, or the electrode chemistry, and even the form factor, whether it's a cylindrical cell, pouch, or a prismatic cell. So, depending on each of these factors, your cells will have different pressure requirements. Sometimes you need a soft material to help with this breathing process to make sure your capacity or your cell capacity does not fall. Sometimes you need a very rigid material. So, all of this can be managed through polymer foams. As Saint-Gobain, that's one of the key products we are offering in this area. So, I'm going to talk more about that. So from this overview, we said there are two things which are important: making sure that the dimensional changes are accommodated irrespective of the type of cell you have, and then ensuring there is optimal pressure on the cells. So there is no one size fits all solution, unfortunately. This we have learned through design and development with several of our customers. Whether it's a type of cell or a type of chemistry, the pressure requirement is different. So in the EV space, particularly for the batteries, we haven't been able to offer one standard product off the shelf saying that, yes, this is what would work for this. So though our goal is to get to a stage where we can offer some standard solutions, it involves some kind of customization and development usually. So the earlier on we are engaged in the design phase, it's much more easier to make sure the right product is provided to our customers. So looking at this example here, so usually the process starts with defining the kind of requirement. The type of cell or the chemistry kind of dictates those requirements. And what does that translate to us? As a materials provider, we're talking about polymer foams here. So the requirement from our customers translate into the type of polymer we would use, how much of cross-linking we need to have, what kind of molecular weight you need to have, do we need to have fillers, or whether we need to provide a softer foam or a rigid foam. So this forms the basic matrix. And then the type of matrix materials used define the microstructure, which kind of translates to the properties we will get eventually. So it's kind of a loop. It starts off with the application requirements or the technical requirements of the type of cell, and then we design the polymer matrix or the micro to provide a certain specific microstructure, which can provide you the properties you're looking for. So this works mostly for the compression requirements, but having the ability to manipulate or formulate these polymers from basic raw materials, we're able to modify it further to add multifunctionality. So that's where the second layer of protection kind of comes in, related to thermal management, where we are not just limiting the performance of our materials to provide a certain amount of pressure, but also some amount of thermal propagation or thermal management. So specifically over the past couple of years, we have designed as a polyurethane-based series of foams with various flame ratings and various densities and thicknesses to address this challenge in the e-mobility, ESS, or EV charging market. So one important factor here is that these foams are engineered to provide mechanical cushioning, and it's very important to have that constant deflection force. So there are lots of polymers. Um, there are much cheaper polymers, and then there are other polymer foams, for example, silicone foams, which are much more expensive. The question is, why should I choose polyurethane foams? So the key factor is to have a constant deflection force. So once you have a cell in a pack, from the time it starts charging to the end of its life, okay, let's say it's about 10,000 cycles, whatever material you use as a compression pad between the cells or a group of cells, it should not lose its structural integrity, where it would kind of maybe lower the pressure requirement on the cell or help damage the cell in some cases. So polyurethane foams are very good in maintaining a constant deflection force. So they have very good compression set. Means over a prolonged period of time, they don't lose their structural integrity. In addition, there's also good dielectric strength, which is very important for safe electrical operation in packs. And in addition to that, we specialize in tuning the features of these polymer foams. The density can be a wide range. Again, depending on the type of cell, we could adjust what density is required, what thickness we can make it at. And sometimes the surface texture also plays an important role when you're considering cost impacts. For example, you have a foam and you need something to stick it, make it sticky so it could stick to the battery cell, right? So we have the ability to make the surface tacky or coat an adhesive in line to help minimize the cost. And sometimes to help with automation, some of our customers come in and say, well, we need the surface to be non-tacky so our robots can pick and place it easily. So we have solutions for that also. There could be a permanent liner which is added, or the surface made non-sticky. So these are some of the ways we customize uh, the products, which are specially used for cell-to-cell compression pad applications. So talking about compression pad applications, what is the property we measure and how does that translate to your pressure and force requirements? So when measuring the common lingo is we use for to talk about compression pads is compression force deflection. This is not the first time you compress your foam. That's if you look at the curve here, you take a piece of foam, you compress it. The initial compression is your force to compress, and then if you hold that at the same strain rate for about a minute, there is some stabilization. Your force value falls and then it becomes stable. So at the end of a minute, we measure the stress again, and that's called the compressive force deflection. And here you see a stress strain curve of several of the polyurethane foams, which I just spoke about. Depending on the density, you can see the response, the compression force response here. So more rigid foam will have a higher force value compared to a much softer foam. Overall, in battery cell and pack applications, what we want is to have a flatter curve over a long uh, strain period. For example, between 10 to 60% or 10 to 70%, you don't want your force values to go up too much. So we have been at work on this for quite some time now, and we've been trying to map out what foams or what densities would work for which type of form factor or maybe the type of chemistry, cell chemistry. I'm not going to get into the cell chemistry part yet because that's a work in progress. But so far, we've been able to kind of map out the force requirements for pouch, prismatic, or solid state batteries. So in this graph here, you see a summary. For example, take one of the products called PF27200. That's the lowest density. It's whenever your pressure requirements are much lower, that is the right solution to use. Whether you're applying 20% or 50% or 70% compression, you can see what the pressure range will be. So it doesn't jump up from, for example, it doesn't go from 10 to 1,000 or something. So it's within a reasonable range between your beginning to end of life. The same way, some pouch cells or prismatic cells are much more rigid and they need more pressure. So in that case, we have our products with a higher density, which can, yeah, this box here, which can provide your initial beginning of life pressure value itself is close to, let's say, 100 kPa, and then go up to 1,000 kPa. Whereas in solid state batteries, we're seeing that the pressure requirements are much more higher. It starts at about 1 megapascal, but within 1 to 4 megapascal, we want a flat curve. So this is where the customization comes in handy. And in some applications, there is also an additional requirement about flammability. So some of our customers want V0 rated products within the pack. So polyurethane foams have some restrictions when it comes to the flame rating. We cannot get a V0 rating unless we go to very high density. For example, 350 kg per cubic meters. That's the minimum density we need in a polyurethane foam to get to a V0 foam. Whereas silicone foams have this high flame rating, they also have high temperature resistance. So we offer both of these. But in terms of cost, the advantage is to use a polyurethane based solution because it's much cheaper and provides you a wide stress strain curve. Talking about the polyurethane foams, I want to share a case study here, is to kind of relate how this translates to the performance. So we have this product PF47250, which is used in some cell-to-cell applications by a few of our customers. So the customer came to us asking for some validation test to confirm, okay, let's take 3,000 cycles, and I want to make sure that this product which I'm using does not lose its performance, uh, mainly the pressure or the thickness, or the structural integrity, irrespective of the temperature range. So we did this test at room temperature 60 degrees and at minus 20 degrees. So we did cyclic fatigue tests and measured the thickness before and after. And we also measured the stress strain values. And you see this curve here is just at 60 degrees Celsius between cycle 1 and cycle 3000. There was a little bit of a drop between the first 100 cycles because it's a polymer material, so there is some lag there, but it's very resilient. But after the 100 cycles, it did not grow. The hysteresis is much shorter. That's what this graph is showing. And then this is a summary of all the three different temperatures. At different temperatures and after 3000 cycles, you can see there's been not much of a material loss. The foam is still intact, no visual damage. The thickness loss was less than 3%. And then the stress drop was stabilized within after the first 100 cycles. So there was no significant pressure or stress loss, irrespective of the number of cycles here. This is very important when you're talking about cell-to-cell applications. So this was custom made for a particular type of battery chemistry and form factor. The same can be repeated depending on what customers are asking for. Any questions on this so far? I will transition to the thermal aspect now. So similar to the compression, thermal propagation is kind of a tricky factor as well, depending on your cell chemistry and the form factor. It's something which is very important to manage. If not, it could be a very costly issue to resolve. So having the right kind of barrier, thermal barrier between cells or a group of cells can help mitigate the thermal runaway propagation in case of a thermal runaway event. So here, through modeling, what we're trying to show here is without any thermal insulation, you can see once the cell goes into thermal runaway, it spreads to the rest of the cells very, very, very quickly. In this case, it was about 4 minutes. Adding one layer of material can help slow that down. But again, if the right choice of material is not used, it could continue the propagation, but at least your time has increased. From 4 minutes, it has gone to 13 minutes. Whereas if you have the right kind of material, your thermal propagation can be delayed or stopped. Stopped is kind of a stretch goal depending on the type of cells. It's really challenging. And then the cost also plays a little bit of a role here in getting the right kind of thermal propagation, thermal prevention material. So, but there are cases where if you have the right kind of thermal barrier, you can stop or delay the propagation significantly. So as material providers, what we are trying to do is kind of manage both the thermal and the mechanical requirements together. So this is a test here of a material we used on an NMC 622 battery pack. So I took a group of cells, put some material in between one of them, and within 6 minutes, it burnt off. And then we used a second material, TRP 1000, repeated the same experiment, and then the second cell is what went into thermal runaway. And here you can see the time was much more prolonged, and only one of the cells, the adjacent cell, is what went into thermal runaway, and the rest were fine. Um, this was an example where we were trying to test various battery chemistries and different types of materials. With NMC 622, one of the materials which we used failed, whereas when we used an NMC 532, the same material worked pretty good and stopped thermal propagation. Another thing we also found out, but I don't have any images here to share, is the type of vent and vent design or the vent size can influence your thermal propagation significantly. In NMC 532, the vent was much more bigger, and it was designed in such a way that most of the projectiles during an event would be going in a certain way. So it had a certain path. Whereas in the NMC 622 battery, that wasn't the case, which made the propagation go on pretty fast, happen fairly quickly. So that was another thing which we were trying to understand and design or recommend products based on not just the chemistry or the form factor, but also the type of cell design itself. Where is the vent located? How big is the vent, or how is the vent designed? Recently, we have come across some of our customers where they're trying to design the vent towards the bottom of the structure. What I'm talking about is automotive OEMs. So in a vehicle, it's very, very important. In case of an event, all of your cells are facing upwards towards the passenger or the driver chamber, right? So that's where the time from the time is very important. From the moment there is thermal runaway, the time it takes for the person driving or the passengers in the vehicle to get out, at least 5 to 10 minutes is required. So we try to prolong that. Whereas if the vents are designed in a way that the time can be prolonged much more further with minimal thermal insulative materials, we can prolong the same time from 5 to 20 minutes or more. So in Asia, we've come across some OEMs working on redesigning the vents, where they're trying to design the vents which face towards the road or towards the structure of the vehicle or the frame of the vehicle. So in case of an event, there is still a lot of time for the passengers to get out. So considering all of those, we try to design the right product. And another important thing which we've also found is the TRP material thickness plays an important role. So I don't have the value here, but I think it was 1.5 millimeter was the product which was used here. And then when we repeated this test with a 3.2 millimeter product, it stopped the thermal propagation. So the thickness also plays an important role. These are some factors to consider. So here, a similar map of the thermal runaway materials. There are some which are polymer-based, but silicone-based are the more popular materials here because they have a V0 rating. So that provides some initial protection because of the higher flame rating and also higher temperature range. So TRP 1000, TRP 5000 series are some of the products we use here. And again, we're talking about pouch and prismatic cells. There is mechanical component and there is a thermal component. So how do we marry these two properties to provide the optimum solution has been kind of the basic strategy for us in our development activities. I don't know how we're doing on time, but want to just go over some of the product highlights. This is the most basic material, I would say, basic product we offer today, which combines the mechanical and the thermal properties to some extent to delay the thermal propagation and also provide good mechanical cushioning if used in cell-to-cell applications. It's called TRP 1000. We have a mica layer and we have a foam here, a silicone foam. This foam, silicone foam, can be replaced by a polyurethane foam if the cells used are LFP cells, where your temperature range itself, wouldn't exceed more than 600 degrees. Whereas if it's NMC, your temperature ranges are more than 600, close to 800 or 1000. So we would go with silicone in that cases. So this is one of the key products we've introduced to manage cell-to-cell thermal and mechanical propagation. And the second one is more like a back cover. It's a solid silicone based material where many of our customers don't make the cells, so they don't have a cell to cell requirement, but they have modules which are put together in a frame. And all that they're looking at is a pack level or a module level cover. So this is a flexible material. It acts as a blanket. Again, depending on the placing of the vent, we can design some ports for the venting gases to exit, or we could have it completely insulated. So this material can withstand temperatures up to 1300 degrees Celsius for over 30 minutes. And this 1300 degrees at 30 minutes was I think 1 millimeter thickness product, but we do offer this product at very thin gauges from 0.5 millimeters to 2 millimeters. So this is some example of the flame testing that was done on this material. Torch of 1300 degrees Celsius for about half an hour. You can see in the backside there is nothing. There is no damage to the product and no propagation. It's fairly intact. Whereas this is a competitor product, you could see kind of burned through, had more scratches. And in terms of the temperature insulation properties, it was much higher compared to this particular product, which we tested here. At 1.5 millimeters, the backside or the cold side temperature was about 400 degrees Celsius. Whereas an alternate, one of them is mica, just a sheet of mica, and the other one is a similar product from a competitor. The backside temperature was about 500 degree or close to 600 degrees Celsius here. And lastly, a sponge, which we use for some thermal mitigation. This can go between cells or towards the end or also as a blanket. It's very good to seal certain vents. So we have some applications where it's used as a vent gasket. So this material has a property where it ceramifies when you apply heat. This is a torch test of about for 1100 degrees Celsius for 30 minutes. The material ceramifies. You could see some cracks, but it does not burn through. In another test we did on this product, at 1600 degrees Celsius, the material did not disintegrate at all. It just ceramified and becomes more of a rigid ceramic from a soft polymer sponge. So these three are kind of the key products we have which can mitigate both the thermal and the mechanical performances. To summarize the loop or our process which we follow, we rely a lot on simulation and we do a lot of live cell testing also. Many of the times the customers' inputs, the technical requirements kind of define which path we start with. Sometimes we start with simulation, sometimes we just take a material, and then depending on the type of requirements, we do some proxy testing or live testing. And then this feedback loop kind of helps us get to a product which is the most suited for a particular application. So with that, any questions?